Statistics, it's all about data, and we're going to be doing things with data, numerical sets of data pretty much. And our general idea is if you see a bunch of data items like this, data values we call them, one of the things we always like to report, as you look at all these numbers, is if you arrange them from smallest to largest, what would be the center of the data set? What would be the middle one? And we have three different ways that we like to calculate, or 3 or 4 different ways to calculate the middle. And mean would be one of them. It's the arithmetic average, the median, and the mode. And there's also the mid-range. So we'll look at how you would calculate those by hand and by calculator. And this first section, instead of going and calculating statistics, we'll be looking at some of the more common graphs that we use in statistics. Some that you've probably seen before, and others that maybe you haven't seen before. So they start talking about a random sample, and most of the studies that are done, polling and that kind of thing, are done with a sample. It's a random sample. The only way that we can ensure that the sample is meaningful is if it's taken at random. Random is essentially putting every element in a hat, and then every possible element, every possible citizen, if you're doing a survey of the US population, and then they randomly select people from the larger group in a random way. We hope that if we take that random sample that we get a smaller group. Kind of looks like this. Here's the entire population. And for example, in the US population, there are 331 approximately million people. Well, if we're going to do a study, we want just a quick estimate of what people are thinking, or an average of this group. We're certainly not going to go contact all 331 million people. So what we do instead is we take this tiny little sample over here, and this is the random sample that they're talking about. And then we calculate, a statistic, maybe the mean or the median or something like that. And then what we do is we say, since this sample is taken randomly, that it's going to be just like the population. So it's a good estimate of the population. And if you ever take a statistics class, that I would recommend that you do, it's because it's useful stuff, and most jobs out there will use it in some format or another. It turns out that this mean that we calculate from the small sample accurately predicts this population fairly accurately, within a small error, the margin of error. And so we do a lot with taking these samples and predicting results. So as you see, leading up to the election, you might see that they're taking polls of US citizens, and they take them in each state to find out, how the states are going to vote as well. If they take 1,000 people from a population of 331 million, and if they find that, let's just use Donald Trump here, because he's definitely going to be the presidential candidate, or at least there's a high probability that he is. Let's say that 470 people say that they're going to vote for Donald Trump. Well, then what we would do, this is just from a small sample, we would take the 470 and divide by 1,000, and that would be 0.47. And then we would say, oh, based on this survey, 47% plan to vote for Donald Trump. And they do these every week, because as you get closer to the election, that's what you really want. You want these polls closer to the actual election day, because they probably are more accurate. But they're accurate most of the time, 95% of the time, but once in a while you get a bad result. And that's what we need to know about statistics. All right, so this unit that you're going to get on statistics is just kind of the basic calculation of a couple of statistics, and some of the common graphs that we use to graph data. So you have data values. These are numerical data values, and they said here that you see an 11 here and 11 here. Those are two individual data values. If these are students that work part-time, or maybe they're going to college and they're taking credits, these are two different students that just happen to be taking 11 credit hours that semester. And then 17, the student's taking a big load. So is this one 16? There's a couple of 16. And you see a lot of 14s. That's a common number. And you can see in that 5 different data values are 12. And so the data value 12 occurs 5 times. Now what we like to do with all this data is we like to arrange it so we can work with it a little better. And so we put it into a frequency distribution. And you can think of a frequency distribution as a frequency table. It's really a table of values, but the columns are such that it summarizes all the data that are kind of spread out all over the place, like this. So the data values are listed in one column. And in the next column, we're going to label the frequency. The frequency is how frequent these data values occur. Another word that we use for frequency is count. So we just count up the data values of that type. So let's take a look at what this would look like in a group of 30 male college students. They asked them, you know, how tall are you to the nearest inch? And they either they either ask the male college students, it's like they asked them. They could also measure them. And here we have, and it says construct a frequency distribution for this data. So when they say something like this, they want you to generate this table. Now what has to appear in the data value column is a listing of all the possible data values. So we go through this list and we're going to pick out the smallest data value. That's called the minimum. I'll abbreviate it min. Looks like we got 60s and 70s. There's a 66. Yeah, okay, so the minimum is 66 and the maximum is the largest data value. There's a lot of 70s. Are there any 80s? I don't see anybody that tall. So 72 is 6 foot. Looks like there's a 75 in there. Is there anything larger than 75? Here's twice. Okay, so I think the max is 75. So it's important to identify those because if you do, then you know the possible data values that are there. So I'm just going to go ahead and start with 66 and just write every single data value from 66 up to 75. And we'll stop right there. All right, so the next column then is you just go through the list and you count. You count the number of data values. All right, so we can do that and it would take some time, but let me show you, because we're going to be entering data into the calculator so frequently, why don't we just go ahead and do it for this example. And I'll show you how counting these up can be much easier. We're also going to want to enter the data into the calculator if we do something else like calculate the mean and the standard deviation of a set of data like this. So I'm going to go enter in all of these data values just like we would in what we've done in other sections of this course. So go ahead and hit the stat key and then edit, and you'll see the lists. This should look pretty familiar to you. All right, I'm going to delete everything in L1 and I'm going to put all these numbers in L1. Clear, and then enter. All right, so starting with 72, I'm just going to enter them in. Doesn't matter the order. We're eventually going to sort them so we can construct that frequency distribution pretty quickly. All of these data values are heights. They all have the same meaning, so it doesn't make sense to throw them into two different lists. We're just going to put all of these data values in a single list. And just to check after we're done typing all these data values in, we'll go through them just to make sure we didn't make any typing errors. And then the other thing that we'll do is we'll actually put the cursor right in the last spot, and you can see that 71 is in position 30. So that means we have 30 data values, and that's consistent with what they said we had. So just scroll through your data list and make sure that you have all 2-digit numbers. It's very easy to type in an extra character somewhere, or leave a character off. All right, so one thing that we can do that would make our job easier to count up these frequencies is to sort the data list. And we're going to sort it in ascending order. So all of these data values are in L1. So I want to tell the calculator to sort, and the A means ascending order, all of the data values in L1. And then we enter that onto our home screen and hit enter. So let me show you where that is. First thing I'm going to do, just so you can see, I'm going to highlight L2 and then type in L1 down here. So when I say L2 is equal to L1, it's just going to make a copy of the first list. See how these are all the same now? I made a copy of this. All right. All right, now I want to go give this command right here, this sort command. All right, so it's in the stat menu, and it's in this very first menu here. You see it there? Sort in ascending order, number 2. So when I hit number 2, it flashes to my home screen, and then I want to sort list 1. Now there is L1, is right above the number 1. L2 is right above the number 2. L3 is right above the number 3, and so on, 4, 5, and 6. We have 6 different lists. If I want to sort L1, then I have to tell the calculator to type in L1. It's blue, and so if we ever want to use a blue key here, we have to hit the blue second key. So I'm going to hit second and then the number 1, and that gives me L1 here. That's it. And then just hit enter. Nothing interesting happens on your home screen, but it did say that it did sort your list. So let's go back into the stat menu and then hit edit so that you can go take a peek at your list. All right, you see this new list now, L1 has been sorted. Here was what it originally looked like. These data values were all over the place, but this is what it looks like now. And when they're ordered, it's much easier to, let's see, to count them up. Okay, so there's 166 and then no others, so I'm going to put a 1 in this column. I have 1, 2, 3, 67, so we're just counting them up. We're not adding them up, we're not summing them up, we're counting them up. So 68, there's 1, 2, 69, there's 1, just 1. All right, 70 is the next one. All right, so for 70, we have 1, 2, 3. And for 71, 1, 2, 3, 4, 5, 6, 7, 7. 71s. It's much less likely to make a mistake if you have them ordered like this. All right, 72 is the next one. 1, 2, 3, 4, 5, 5. 72s. And we have 1, 2, 3, 4, 5, 5 73s, a 74, and 2 75s. Now, hopefully, when we add all these frequencies over here, they should all add up to 30, because we do have 30 males in our grouping. All right, and then number 21 says to construct a histogram and a frequency polygon for the data. All right, so a histogram is like a bar graph, and a frequency polygon is, it's an XY, it's a, you know, or Cartesian, connect the dot graph, Cartesian graph. So for a histogram, the general shape is going to look like this. Something like that, a bar graph. And the frequency polygon will look something like this. Connect the dots. Okay, so what we want is we want these numbers along the x-axis, the data values, and then the frequencies will be along the y-axis. So it's going to look something like this. I'm going to make a big long x-axis here. But this would be your heights. Always label the axes, and the heights are in inches. And the vertical axis is the frequency. Just the count. So as we look through these frequencies here, the highest frequency is 7. That occurs when the height is 71. So we want to make sure that our vertical axis goes up to at least 7. All right, now our data values, our heights, they begin at 66 and they go up to 75. And that makes 10 different values. So usually on the horizontal scale, if this is not 0, then we'll put a little break mark to indicate that, you know, hey, we're not dealing with the, this is not really the y-axis. There's a break in the axis. So something like that. So this one, and these bars are going to be connected together. So there's going to be no gaps between the bars. And then 68 would be 2, and 69 would be 1, and 70 go up to 3 again. And the number is kind of right in the middle of the bar in each case. And 71, here's where we jump up to 7. And then down to 5. And then another 5. And then back down to 1. And then finally 2. All right, so that's what it would look like. Now for the frequency polygon, this is another graph. I'm not going to draw a new graph or a new axis or anything like that. But what you basically do is you create an ordered pair with the data value and then the number, the frequency, the data value and the frequency, and so on. And do this for every single row of your table and plot those points. Well, let's just plot a couple of them. Where does the point 66.1 fall? So here's 66, and there's 1, so the point 66.1 would be right there. The next point is 67.3. Here's 67. If you go up to 3, you're right there. The next one is 68.2. So here. And if you look at this pattern, you can see that the points that we plot for this frequency polygon appear precisely in the top middle of each one of these histogram boxes. So if you just continue that pattern, you'll see the dots that you use to draw the frequency polygon. And this is what a frequency polygon looks like. And so what we do is just to connect the dots, and then this is your graph. Sometimes they recommend to just kind of extend this graph one more point and put it on the horizontal scale and extend this one down, but we'll just plot the points that are given to us there. So yeah, those are two graphs that you'll see in this section. You'll be given different sets of data, and you'll be asked to construct similar graphs. All right, so this problem over here with taking a random sample, the idea is to get a representative sample. And so they'll ask you a question like this. Imagine that you want to get the views of everyone in the large city. And you want to know whether the residents will support the building of 3 new schools. Now, that's not a deal around here because the population of Michigan is shrinking and everyone's leaving the state to find jobs elsewhere. But in some areas, some of the bigger city areas, a lot of people are moving into the cities, and because of that, some areas, for example, down in Texas, they're building new schools on the rate of one every year, just because there's so many people moving into the area. So the council decides to conduct a survey of a sample of the city residents. Which procedure would be the most appropriate for obtaining a sample of the city's residents? And just remember, these city residents live all over the place. Would it be appropriate to survey a random sample of teachers who live in the city? After all, it's new schools. Would it be more appropriate to survey 100 individuals who are randomly selected from a list of all people living in the state in which the city is questioned? The city in question is located. So would the result of this survey lead us to the most appropriate result? C would be to survey a random sample of persons within each neighborhood of the city. And finally, survey every 10th person who enters City Hall on a randomly selected day. Okay, which of those 4 methods do you think would be most appropriate if you wanted to get a sense of whether the residents of the large city would support the building of 3 new schools? Yeah, I mean, if you want the view of all citizens, then it doesn't make sense to ask only teachers. If you're interested in knowing the views of the folks in the city, then you certainly wouldn't ask everyone in the state. And the people that go into the city hall, they may or may not be from the city. They might be from some other region. They might be a worker that's going to work in the morning and they don't even live in the city area. So yeah, this is the correct one, a random sample of the people who are going to be affected. And the fact that they're asking people in every neighborhood, that means every neighborhood of the city will be represented in the survey. So yeah, that's the correct one. Okay, so in addition to constructing these frequency polygons like this, see how they just kind of dip this down to the horizontal axis, and the same thing over here. Sometimes they do that. It's not required. These are the distribution of IQ scores. All right, so look at this graph here. Number of people, that's the frequency. That always goes on the vertical axis. And then these numbers here are IQ scores. And you measure just about anything about the human population, just about anything, you're going to see this graph that looks like this. And it's called a bell-shaped curve because it kind of looks like a bell. The top of it anyway. And this will be the topic of section 12.4. We call this the normal curve. It occurs normally in the general population when we study lots of things related to the human or plant life. IQ scores is one. Most everybody, the highest percentage of people are kind of in the middle, but you have some folks that have very high IQs over here, and you have some folks with low IQs over here. But everybody is mostly in the middle. So this one, instead of constructing the frequency polygon, you're asked to interpret stuff about. All right, so take a minute or so and write down some answers to these 4 questions. The graph is based on a sample of approximately 50 people. True or false? More people had an IQ score of 100 than any other IQ score. As the deviation from 100 increases or decreases, the scores fall off in a symmetrical manner. More people had an IQ score of 110 than a score of 90. True or false? And the percentage of scores above any IQ score is equal to the percentage of scores below that score. True or false? Yeah, so this isn't a frequency distribution, but we can interpret each one of these points and actually construct this frequency distribution. And the reason you might want to do that is, to try to figure out if this first one is true or not. And so I'm just going to go to 100. It looks like there's about 28. Go over there. It's about 28 is at the peak. And these two are at the same number, 25. And if you just count those middle 3 categories, you can see this is like 78. So already we've got 78 individuals scoring just one of these 3. So the graph is based on a sample of approximately 50 people. That is false. We can already see that 70 some would make this up. Okay, so here's your max. And that does correspond to 100. So more people had an IQ of 100, true, than any other IQ score. And as the deviation away from 100 increases or decreases, the scores fall off in a symmetrical manner. That's exactly what's going on here. That is true. More people had an IQ score of 110 than an IQ score of 90. Well, here's 110, looks like right there. Here's 90, right there, it's 20. So in fact, both at 110 and 90, they had an equal number. More people had an IQ score of 100. Okay, that's got to be false since they have the same number. The percentage of scores above any IQ score is equal to the percentage of scores below that score. Yeah, we can see that that's false. So for example, if we take the data value 120, here's 120. The number of data values higher than this would be these folks here, maybe these 3 folks here and these 2 folks here. So only 5 individuals had an IQ score higher than 120. Well, over here, we've got, in the hundreds probably of folks that have an IQ score less than 120. So when it says that the percentage of scores above any IQ score is equal to the percentage of scores below that score, that's false. The only time it ever works is at 100. At 100, you're going to have about the same number over to the left as you have to the right.